All right, let's get started. It's my pleasure to introduce Dr. Miyasaki. Miyazaki-san earned his Ph.D. in geophysics from Tohoku University in Japan and went on to a postdoc at JAMSTEC, which is the Japanese Agency for Marine and Earth Science. He was a visiting scientist at KNMI in the Netherlands and at the International Pacific Research Center in Hawaii. He is currently a senior scientist at JAMSTEC and a visiting scientist at JPL. Miyazaki-san is a leader in the field of chemical data assimilation, and he has been very successful in assimilating multiple chemical species from several different satellite instruments. And I'm honored to have him here to present the results from an 8-year reanalysis of tropospheric chemistry.
Can you hear me? Is it working?
I think so.
Yeah. So thank you very much, Helen. So first of all, I'd like to express my appreciations for giving me this opportunity. So I have been working on the data assimilation of chemical compounds in the atmosphere. Then recently I have conducted the 8 years chemical reanalysis calculations from the assimilation of OMI, MLS, TES and MOPITT data. So today in this talk, I'm going to talk about the basic idea of chemical data assimilation and my recent results obtained from this 8-year reanalysis calculation. Okay, so this is the introduction of my talk. So the long-term records of the chemical compounds in the atmosphere are very important for understanding the changes in the atmospheric environment and their impacts on changing climate. So there has been the increasing interest or importance in developing the method for combining the different sources of information obtained from satellite measurement to provide the better knowledge on the atmospheric environment variations. But the combined use of the different data set is not so easy, because the information that may be obtained from the the use of the multiple satellite data sets is limited, related to the different vertical sensitivity profiles and different overpass time and mismatches in the space and spatial and temporal coverage between the instruments, as well as the missing information on the chemical region and origin of air masses. So we need a very good technique to combine the various sources of information obtained from satellite. So we use the advanced data assimilation technique to combine the observational information. The purpose of data assimilation is to extract the signal from noisy observation and to interpolate in space and time and to reconstruct state variables that are not sampled by the observation network. Then in the chemical data assimilation, we do make best use of all available data from the heterogeneous sensors scattered in space and time. Then we extend analysis on non-observed species and space. Then because of these processes, we can produce the chemically and dynamically consistent integrated data set from a combined use of the different observational information. Then there are many important applications of chemical data assimilation, such as the air quality monitoring and forecasting and emission source inversion. And also the chemical reanalysis is a very important topic in the recent years, because the chemical reanalysis data can be used as the input to the climate simulations, or can be used to validate the chemical transport models. So in Japan, I myself, I've been working on the development of the chemical data assimilation system. So I have developed the chemical data assimilation system using the Ensemble Kalman filter technique to combine the observational information obtained from the various satellites and using a global chemical transport model. Then this data assimilation system simultaneously optimizes the several emission sources of ozone precursors and the chemical concentrations of all the predicted chemical species in the troposphere. Okay, so here is the summary table of the data assimilation system that I developed in the past, so far. So the data assimilation technique is based on an ensemble Kalman filter technique with the 48 ensemble members. And the forecast model is the Japanese chemical transport model, CHASER, which includes the 47 chemical species in the troposphere and calculates the 88 chemical reactions. Then the horizontal resolution of this model is T42 with about 2.8 degree spacing. Then the a priori emissions are constructed based on the emission inventories from the Edgar, Geyer, and the GFEDO. Then the state vector in the data assimilation includes includes several important emission sources of the ozone precursors, as well as the concentration of 35 chemical species. The observation operator includes the averaging kernel and the a priori information. I will discuss this more in the next slide. Then the spatial resolution of OMI and the MOPITT is much higher than the model resolution. So we have developed a super observation technique to have the more representative data before data assimilation for these measurements. Then the data assimilation cycle is 2 hours. This is very short compared with the data assimilation window used for the long-lived species such as CO2. But this setting is very important to reduce the discrepancies between the observations and the model under the presence of the very fast chemical reactions in the troposphere. Then I have assimilated some measurements obtained from the OMI-NO2 from the Dutch Domino project and TES ozone version 5 and MOPITT CO version 6 and the MLS ozone and the HNO3 version 3.3 data. Then to validate the analysis results, I have used some independent observations, including the satellite and the aircraft measurements. Okay, so here I'd like to very briefly introduce the Ensemble Kalman filter data assimilation technique. So in this technique, the forecast error covariance or the background error covariance is estimated from the Ensemble model simulation, so which contains information about the uncertainty in the model forecast. So because of this, the so-called the flow-dependent forecast error covariance, we can take full advantage of the chemical transport model in the data assimilation analysis. Then here are some important equations of the Ensemble Kalman filter technique. So first, the background ensemble mean and its perturbations are obtained from the evolution of each ensemble members using the forecast model. Then the background error covariance used for the data assimilation analysis is obtained by assuming that these background ensemble perturbations sample the forecast errors like this. Then to have the observational constraint were to be compared with the model forecast, to be compared with observations, we have developed the observation operator like this. Then this will be discussed in the next slide. Then the analysis ensemble mean and its perturbations are obtained by updating the background ensemble forecast, background ensemble informations using this analysis error covariance matrix. Then in this analysis, the analysis ensemble spread information can be regarded as the uncertainty of the analysis fields. So this kind of information can be obtained from the Ensemble Kalman filter data assimilation approach. Okay, so for the assimilation of satellite retrievals, we need to develop the observation operator corresponding to the characteristics of each measurement. So this observation operator H converts the model profile X to the profiles that will be retrieved from satellite measurement, YB. Then here, the H is the observation operator. Then the XA is the a priori information used in the satellite retrieval. Then the A is the averaging kernel matrix for individual measurement. Then the S is the spatial interpolation operator. So because of this, the observation operator, the model satellite difference is not biased by the retrieval approval profiles. So we can have the adjustment toward the true atmospheric states with the consideration of the measurement sensitivity. So this information is used in the analysis step of the data assimilation. Then these are the typical profiles of the averaging kernel for each assimilated measurements. Okay, then this figure shows how the individual measurement provides information on the different aspects of tropospheric chemical system. So first, the MOPITT CO data is used to constrain the surface CO emissions, then which influences the oxidation capacity of the atmosphere, and as well as the chemical lifetime of the several important greenhouse gases or chemically active species. Then the OMI NO2 data is used to constrain the NOx sources at the surface and also by lightning, as well as the concentration of some nitrogen species in the troposphere. The concentration of ozone and some chemically related species are constrained from the assimilation of TES ozone and MLS ozone and MLS HNO3 data in the troposphere and in the lower stratosphere. So, as shown by this figure, the combined use of the various measurement with the different vertical sensitivity is expected to distinguish between the surface emission sources and lightning NOx sources. So the estimation of these sources will be discussed later in this talk. Okay. Then the state vector used in the data assimilation analysis includes the several important emission sources, as well as the concentration of 35 chemical species. Then the background error covariance matrix, as estimated from the Ensemble model simulation, determines the relationships between the different chemical species concentrations and between the relationships between the emission sources and chemically related to species concentrations. So this is an example of the estimated background error covariance matrix for the tropics at the ground surface and at 500 hectopascal. So this matrix shows the very strong correlation between the surface NOx emission sources and the chemical concentration of ozone, NOx, and some nitrogen species. So this implies that the capability of the measurement of these chemical species to constrain the surface NOx emissions in this analysis using the background error covariance matrix. Then here it is important to mention that the covariance among the weakly related species is neglected in the analysis to remove errors in the ensemble sampling. This is very important because the ensemble Kalman filter technique always has the problems of introducing the spurious error correlations in the background error covariance because of the limited ensemble size. So this kind of the covariance localization technique is really important to improve the performance of the chemical data assimilation to avoid the unnecessary adjustment from the spuriously produced correlations because of the very small number of ensemble. Okay? So by using the chemical data assimilation system, I have conducted the 8 years chemical reanalysis calculation. Then the long-term stability of the data assimilation performance is very important for evaluating the performance of reanalysis. Then here, the chi-square diagnosis can be used to measure the data assimilation performance, which is estimated from the ratio of the actual observation minus forecast to the estimated background error forecast magnitude, like this. Then these figures shows the estimated chi-square values in the black lines. Then this blue shaded show the number of the assimilated measurement per month during the analysis period for each assimilated measurement. So these chi-square values are mostly close to the ideal value of 1 in most cases, which suggests that the background error covariance is reasonably specified in the data assimilation. But for the OMI NO2, chi-square is much higher than the ideal value of 1, which suggests that the model is, which implies the overconfidence in the model. So because the lower tropospheric NO2 concentration is controlled by the very fast chemical reactions, so which may lead to the underestimation of the ensemble spread in the forecast step. Then after 2010, the chi-square is increased compared with before the previous period, which is associated with the reduction of the number of the measurements used for the assimilation. So having the constant number of observation is very important to have the stable performance of the reanalysis for the multiple years. Okay, so these figures shows the time evolution of the zonal mean observation minus forecast statistics obtained for each assimilated measurements. Then this OMF was estimated from the model forecast without any data assimilation. Then this is the result for the reanalysis calculation. So as you can see here, the persistent model errors can be found in the underestimation of the tropospheric NO2 concentration as compared with OMI NO2 measurement in the northern hemisphere and in the tropics. And also the underestimation of the tropospheric CO concentration can be found as compared with MOPITT CO measurement in the northern hemisphere. Then the ozone concentration without data assimilation is overestimated in the extratropics as compared with the TES and the MLS measurement in the middle and the upper troposphere. Then after the data assimilation in the reanalysis, this OMF value becomes nearly 0 in most cases. Then the annual mean OMF becomes almost constant with year, so which suggests that the a posteriori emissions realistically represent the interannual variation of emissions. Yes. Then there is another important information that can be obtained from the data assimilation analysis processes. That is the analysis increment. So this figure shows the temporal evolution of the analysis increment of ozone at different pressure altitude. So these analysis increments are very different between the 700 hectopascal and 400 hectopascal. So this implies that the TES ozone measurements have the almost independent of informations for the lower and the upper tropospheric ozone. So from this data assimilation, we have the potential to correct or to improve the vertical profile of tropospheric ozone from the assimilation of these measurements. Okay, then the data reanalysis performance was evaluated against the independent observations. So this figure shows the comparison against the global ozonesonde observation in July 2007. Then as you can see here, the reanalysis shows the much better agreement with the ozonesonde observations globally. So the biases in the troposphere and lower stratosphere are almost removed after data assimilation. But the remaining errors are large near the surface. So this is associated with the low sensitivity of measurement to the lower tropospheric ozone. So we still need to have the additional constraints on the lower tropospheric ozone from the new measurement or new retrievals in the future. Well, of course, the optimization of the ozone precursors is also important to have the better agreement with the lower tropospheric ozone observations. And here is the year-to-year variation of the ozone concentrations for these regions. Then the observed concentration shows the significant year-to-year variation during the reanalysis period. Then in most cases, the analysis shows the much better agreement with the observed year-to-year variations, like this and this. Then, for example, at northern mid-latitude here, between the 850 and 500 hectopascal, the observed concentration shows the slight increasing trend in the ozone concentration during the 8 years from 2005 to 2012. So this increasing trend is well captured by the reanalysis, but the model in the blue color without any data assimilation shows the decreasing trend during this time period. That is very different from the observation and the analysis. Okay, so this is a comparison against HIPPO measurement over the Central Pacific. So from the comparison against HIPPO ozone measurement, I do not explain the details, but this is most important message obtained from the comparison. So we found that the direct concentration adjustment by TES and MLS and the corrections made to the precursors emissions over the Eurasian continent, especially over East Asia, were both important in influencing the tropospheric ozone profiles over the North Pacific. So the combined assimilation of the multiple species data is the powerful, very useful approach to improve the entire tropospheric ozone profiles, even over such the remote oceans. That is the important message obtained from this comparison. Then, I'd like to here emphasize the importance of the emission optimizations on the analysis of the tropospheric ozone profiles. So this figure shows the seasonal variation of the ozone bias against the ozonesonde observations at the northern mid-latitude. So this is month, and this is pressure. Then this bias is obtained for the reanalysis calculations, where both the concentration and the emissions were optimized from the satellite measurements. Then in another case, in this case, the bias is estimated for the sensitivity experiment in which the emission optimization was excluded from the reanalysis calculation. So in this case, state vector does not include emission factors. It is not adjusted from any measurement in this case. Then from the comparison of these biases, we can say that the emission optimization reduces the negative ozone bias below about 500 hectopascal in the summer season by up to 40%. So the simultaneous optimization of the emissions and the concentration is really necessary to have the better agreement with observations for the entire troposphere. Then I do not show the results for this, but I found that the year-to-year variation of the lower tropospheric ozone concentration is also well represented by including the emission optimization in the reanalysis framework. So the simultaneous optimization approach produces high-quality multiple-year reanalysis data for the tropospheric ozone profiles. Yeah, because most of the chemical data assimilation studies optimize only the concentration fields, But my message is that it is better to include emission optimization together with the concentration adjustment. Okay, so next I'm going to talk about CO, carbon monoxide analysis. So this is comparison against the surface measurement obtained from the WDCC network. So then I selected 12 stations from the network. Then without the assimilation, as in the most other chemical transport models, our model CHASER largely underestimates the CO concentration in the northern hemisphere and also in the tropics. Then the model negative bias is mostly removed by the data assimilation in the reanalysis in this red line. So then the observed concentration shows the decreasing trend of the CO concentration in the most of the northern hemispheric sites. So the decreasing trend is also very well captured in the reanalysis because of the adjustment made to the surface CO emissions in the reanalysis. The CO concentration was not adjusted from the assimilation in my framework. Only emissions were optimized. Then the reduction of the model negative bias of CO can be found throughout the troposphere compared with the aircraft measurement taken from the Mosaic and the Iagos project. So this means the observational constraints provided at the ground surface are propagated well into the entire troposphere. So yeah, this is a very good result. But however, then compared with the HIP measurement over the Pacific, we have some problems still. So this is comparison of the CO concentration. Then most of the negative model bias is reduced in the reanalysis, as you can see here. But the analyzed CO concentration is still too low as compared with the measurement, especially in spring and summer season over the Pacific. Then on the other hand, the analyzed CO concentration over East Asia did not show any underestimations as compared with the ground measurement. So that suggests the remaining negative bias in the comparison obtained from the comparison against HIP measurement could be attributed to the overemphasized chemical destruction related to too much OH concentration in the model, while air is transported from the Eurasian continent to the Central Pacific. So this OH issue will be discussed a little bit later in this talk. Okay. So this is a summary figure of the performance of data assimilation. So each panel shows the improvement in the global spatial correlation and reduction in the global mean bias and the root mean square error as compared with the G's measurement. So in this bottom list, the name of the measurements and the species and the pressure altitude used for the validations are shown here. Then data assimilation greatly improved the agreement with the various species data. So the simultaneous assimilation of the multiple data set is the very good approach to have to produce the data, good various species field, good various species data set. Then to understand how the individual assimilated measurement contributed to the overall performance of the data assimilation, I have conducted the so-called observing system experiment by separately assimilating the individual measurement into the data assimilation system. Then here, each color bars shows the improvement obtained from the individual measurement used in the reanalysis framework. So then, for example, so to have the better agreement with the NO2 measurement here, then the assimilation of OMI NO2 data was most important. Yeah, that's very reasonable. Then for having the better agreement with CO measurement, assimilation of the CO, MOPITT CO data was most important. Then, yeah, this is most interesting results here. This is a comparison against the ozonesonde observations in the lower and the middle troposphere. So in this case, all the assimilated measurement contributed to improve the agreement with measurements. So our approach is an effective way to improve the representation of tropospheric chemistry by influencing the ozone precursors emissions and chemical processes controlling ozone concentration variation. So it can have some benefit by having the constraints from the multiple species observations to have the better estimates of ozone concentration. Then in the tropospheric chemistry system, yeah, as you know very well, the OH is the key species. That is the most important chemical species. Then, it is interesting how the data assimilation modified the OH distribution in the analysis. So this figure shows the temporal variation of OH, tropospheric mean OH concentrations in the reanalysis. And this is a difference from the model. So the analysis increment introduced to the OH concentration. Then this figure shows the OH concentration as a function of latitude and pressure. So the OH concentration is largely decreased in the northern hemisphere and increased in the tropics after data assimilation. So these changes are mostly attributed to the assimilation of the MOPITT CO data in the northern hemisphere and the assimilation of OMI and TES ozone data in the tropics. So these changes in the OH concentration played a very important role in propagating the observational information among the different species. Then recently, from the analysis of the methyl chloroform observation, Patola et al. 2014 estimated the mean northern hemisphere to southern hemisphere ratio of OH concentration in the troposphere at 0.97. This means the OH amount is almost the same between the two hemispheres. Then on the other hand, our model simulation estimated the ratio at 1.26, which is much higher than the observational estimate. But this value is within the value obtained from the acmic intercomparison. Then after the data assimilation, this ratio becomes 1.18, which is smaller than the model forecast, but it becomes closer to the observational estimate. So, but still, this observational estimate has large uncertainty. But these changes introduced by data assimilation may create a positive, may provide positive impact on the tropospheric chemical system. It is the suggestion obtained from this comparison. Then the chemical lifetime of NOx and CO and other species are so largely influenced by the OH concentration. So these changes, including the OH analysis increment, suggest the importance of simultaneous optimization of on the entire tropospheric chemical system and the emission estimates. Yeah, but we are not sure if this correction is made toward the realistic OH field or not, because we still need the more accurate direct measurement of OH in the troposphere, of course. Then here I'd like to introduce the emission estimate obtained from my reanalysis calculation. So these figures shows the global distribution of the surface NOx emissions and lightning NOx sources and surface CO emissions obtained from the a priori emission inventories and obtained from the a posteriori reanalysis calculation. Then in the bottom, the analysis increment So the difference between these two estimates are shown here. So the first, the surface NOx emission, the global total value of the surface NOx emission is estimated at 42.2, which is about 10% larger than the a priori emission. And this 10% increase is attributed to about that 7% increase in the northern hemisphere and the 14% increase in the tropics. Then the right-wing NOx sources, the global total value of these sources is estimated at 6.4, which is about 24% larger than the a priori value. This a priori value was estimated using the right-wing NOx parameterizations based on the price and wind approach. Then finally, the surface CO emission is increased by the 36% globally. And this very large increase is attributed to about 110% increase in the northern hemisphere. So this is a very basic or general structure of the estimated emissions. Okay, so this is my ongoing research. So then I have estimated the emissions for the 8 years from 2005 to 2012. So we can investigate some year-to-year variations or linear trends in the emission fields. Then I found this this trend structure is very different between the emission inventories and my analysis. So I'm now analyzing the detailed structure in the estimated emissions, and this will be my next paper or study. So I do not discuss this today. So, okay. So here I'd like to focus on the surface NOx emission estimations in 2007. So these figures show the annual mean or annual total emission values and the seasonal amplitude of the surface NOx emissions and the timing of the maximum emissions in months obtained estimated for the inventories and data assimilation results, and this is a difference. So the data assimilation introduces the positive increment over the most of the polluted regions at northern mid-latitude, such as over East Asia and some parts of Europe, and also over eastern United States. So these adjustments imply that these emission inventories underestimated the anthropogenic sources at the most of northern mid-latitude. Then the data assimilation also introduces the very large seasonalities in the emissions over most land, as shown by these red colors. So because the emission inventories used as the a priori emission did not consider any seasonality in the anthropogenic sources, but there is some enhancement in the use of the heating or some changes in human activity can cause the seasonal variation in the anthropogenic emissions. So data assimilation introduced such the reasonable adjustment to the seasonality of the emissions. Then the timing of the emission, maximum emission is also significantly modified, especially at northern mid-latitude, which is probably associated with the misrepresentation of the summertime soil emissions in the emission inventories. Then in the multiple data assimilation framework, the adjustment of concentration of chemically related species has the potential to improve the emission estimate. So this was compared with simple inversion based on measurement of the NO2 observation only. Because in this case, the uncertainty in the model chemistry may influence the quality of the emission estimates. So these figures compare the seasonal variation of the surface NOx emissions between the a priori emissions and this multiple data assimilation emission estimation and NO2 observation only inversion. So the emissions estimated from these two different top-down calculations significantly differs in most cases, with up to the 58% difference on regional scale. So the analysis increment means the difference between the analysis and the a priori is generally larger in the case of the NO2 observation only. So because the analysis increment is introduced to compensate for the various sources of errors in this case. But in the multiple data assimilation framework, we can have the comprehensive constraints on the whole tropospheric chemical system. But most of the previous emission estimation used this NO2 observation only. So in this case, the emissions may be overcorrected from the emission inventories. This is a suggestion from my analysis. Okay, so if I have time, I'd like to introduce this result. Shouldn't take so long time. Okay, so finally, I'd like to discuss the NOx productions by lightning in the troposphere. So as some of you may know very well, the lightning accounts for only about 15% of the global NOx sources, but it is the most dominant source in the upper troposphere and can lead to a significant ozone production in the upper troposphere. So the accurate estimate of lightning NOx sources are very important to understand variations in NOx and the oxidation capacity of the atmosphere and the chemical lifetime of several greenhouse gases as well. And from these studies, the lightning NOx sources are simulated to increase in the future climate significantly, and which have a very large influence on the prediction of ozone and also the radiative heating in the future climate simulation. So we need to have the better knowledge on the global total amount of lightning NOx sources and its the three-dimensional distributions for the current and the future climate situation. So this increase in the lightning NOx sources in the future climate is corresponding to the changes in the cumulus convection activity in the tropics mainly. Okay, so the chemical transport models have used the empirical parameterization to determine the lightning and the subsequent NOx formations in the troposphere, like this, as illustrated by this figure. But these parameterizations are so too simplified, and there's so many large uncertainty in the parameterization. So we still need to improve the basic idea of this parameterization. Then on the other hand, the satellite observations can be used to constrain the lightning NOx sources using the top-down analysis framework. So I use my reanalysis system to constrain the global distribution, global 3D distribution of lightning NOx sources. So these figures show the latitude and pressure cross-section of the zonal mean lightning NOx source analysis increment introduced by the reanalysis framework and introduced by the individual assimilated measurement using the observing system experiment framework. So as you can see here, that the overall structure of the analysis increment is dominated by the assimilation of OMI NO2 measurement. But the assimilation of non-NO2 species, like the ozone and HNO3 measurement, also have the great, very substantial influence on the analysis of the vertical profiles of lightning NOx sources. So the combined use of the multiple data set with different vertical sensitivities facilitates the estimation of the vertical lightning NOx profile and to distinguish between the surface NOx emission and lightning NOx sources. So I should note here that the correction made to the lightning NOx sources have the great, very important influence on the estimation of surface NOx emissions, because it can reduce errors in the upper tropospheric NO2 and NO concentration then that reduces the model errors and will improve the surface NOx inversion. So it is important to have the optimizations simultaneously for the surface and the lightning NOx sources. Okay, so then these are the estimated lightning NOx source distributions from the reanalysis framework. And I do not discuss the details, but from the detailed analysis of the estimated lightning NOx source distribution, we have obtained some or several important implications to improve the lightning the parameterizations used in chemical transport model. Then here I pick up only a few very important messages from this slide. So first, the widely used lightning parameterization based on the C-shape assumption with the peak sources in the lower and upper troposphere, underestimate the sources in the upper troposphere, and overestimate the peak source height by up to about 1 kilometer over land, and also over the tropical Western Pacific. Then the power 1.73 in the modeling of the height dependence of the lightning activity over ocean might be underestimated in the price and wind approach. So this implication was obtained from the comparison between the a priori and a posteriori lightning NOx source profiles. Then from the analysis, we have investigated that the tropical thunderstorms might be less effective than the mid-latitude storms to produce the lightning NOx molecules due to lower wind shears and smaller stroke lengths. So there are some other messages, but I'll skip them because it's almost time to finish. Okay, so let me summarize my talk here. The optimization of both the concentration and the emission field is an efficient method to correct the entire tropospheric profile and its year-to-year variation. Then the data assimilation statistics imply the persistent reduction of model error and the improvement representation of the emission variability. Then it was interesting that the OH distribution was modified considerably and became closer to an observational estimate, which played an important role in propagating the observational information among the various chemical species and the emission estimate. Then there are some important applications of this study, I think. So first, the data set produced by the reanalysis framework can provide the comprehensive information on the atmospheric composition variations because it has information on both the emission sources and the chemical reactions in the troposphere. Then this data can provide the initial and boundary conditions for the climate and chemical simulations. They can be also used as inputs to meteorological analysis to determine the relative heating of several important chemical species. And this data can be also used to evaluate the CCMs and bottom-out emission inventories, especially where the observations are not available. This data set can provide some information. Then the statistical information obtained during the reanalysis calculation can be used to suggest the development of the models and observations. Okay, so this is my final slide. Then, I still need to improve my reanalysis framework. So first, maybe important to have more data set to improve the reanalysis quality. Because after 2010, the number of the TES and OMI measurement were decreased suddenly, and it affected the quality of the reanalysis data. So, but we can use some other data sets like the EADS and the EADS data. So it might be good to have more observational constraints. Then, but each measurement have a different bias structure. So it is extremely important to apply the bias correction scheme for the individual measurement. Then the optimization of the additional precursors emissions, such as the VOC emissions, could be also important. Then, of course, the improvement of the forecast model are also important. So I plan to replace my model, Chaser, with the latest one or other model to investigate how the performance model of the model influence the data assimilation result. Okay, so finally, I'd like to express my appreciation for my colleagues. And if you are interested in the details of my study, please have a look at these published papers. Okay, that's all. Thank you very much.
Thanks very much for the informative talk. Any questions?
I really like your analysis of OH. Can you put your picture of the OH? And yeah, this picture. So do you know what other species mostly influence the changes in these bottom two pictures for OH?
Yeah, so the CO was important in the northern hemisphere, and the ozone and NOx is important in the tropics.
Okay.
Yeah.
The water vapor in this simulation, is it just from the
It's not fixed. It's fixed.
It's fixed from the reanalysis?
From the model GCM simulation. Then the GCM is nudged toward the NCEP reanalysis.
Okay.
Yeah.
Also for the water vapor?
Yeah.
Okay.
You're seeing an increase in the NOx by lightning production
Yeah.
because there's more lightning?
Yeah. Yes. So yeah, these studies investigated the increase in lightning NOx sources. From my analysis, you mean the trend or?
Yeah, you're seeing more lightning production.
Yeah. Okay. Yeah. Previous. Okay, so this is this is the trend of the lightning NOx sources during the 8 years. Then this red color shows the positive trend in the source, lightning NOx source amount. So over the Central Africa and the South America, related to changes in the convection activity, there are more lightning NOx sources during the 8 years.
Thank you.
Yeah.
Thank you for this really nice talk. I have a question about sort of the interpretation of your results for these trends in the long-term data assimilation. It's nice that you have included in your state vector both emissions and chemical concentration. And here, like, you're showing the trends and the increments for the emission factors, and we can interpret that as the bottom-up inventories not having the right emissions trend.
Yeah.
My question is, do you have trends also for the increments for the chemical concentrations? And what would be, presumably an increment in the chemical concentration is a correction for some bias in the chemical mechanism or missing chemistry. But if that increment changes in time, what is your interpretation of that? Is our chemical bias changing in time?
Yeah, that's really.
How do we interpret that?
Yeah, that's a really good point. Yeah, that is one of the things I'd like to explore in my next study. But today I can say that the changes in the analysis increment is generally larger for the emission fields compared with the adjustment to the concentration. But the analysis increment for the concentration is not constant with time. It can change a lot with time, with season and with year, which may reflect some problems in the chemical processes in the model, because the model error biases cannot be constant with year because of different atmospheric conditions and different forcing provided by the emissions and some other boundary conditions. So that's a very good point to investigate in the next future study. Yeah, thank you very much.
So that's very nice talk, very nice work. That's impressive. I have a more data assimilation question about your background error occurrence matrix between the variables. So you use, I guess you use a specific localization function between variables, right?
Yeah.
Okay. So I think this localization function will be dependent of your chemical regime, or if you're closer to the source or far from the source,
Yeah.
if it's night or day. So have you tried to use different localization functions? Because if you correlate too much, you might degrade your forecast. If you correlate not enough, you might miss something. So can you comment about that? And
Yes, so the chemical regime is very different between the urban and rural areas. And in my analysis, the localization is also applied for the space. I mean, the very remote observation do not influence the analysis at the point of. So I mean, only the observation which may have the similar chemical regime influence the analysis. So with the the influence distance of 2,000 kilometers, the observational information were excluded to avoid any unrealistic adjustment obtained from the very different chemical regime. Yeah. But yeah, I'm sorry. I cannot explain it well.
Yes, hi. I have a question about your prior emissions. What error did you assume? How did you define them? And did you test different assumptions on your inversion for those errors?
For observational error?
No, prior errors.
Or emissions?
In your emissions, yeah.
Yeah, in emission, we need to have the assumptions about the magnitude of errors and its spatial distributions. And of course, then we do not have any forecast model to the emissions. So we need to add some random errors during the analysis. So I have made a lot of sensitivity calculations by changing the a priori error values and by changing the random perturbation processes during the analysis. Then I had the reasonable value to have the reasonable seasonal and internal variations in the emissions. So that's kind of the tuning factor, because we do not have any strong evidence on the magnitude and structure of the emission sources errors. So it's really trial. But it's about 40% for surface NOx emissions,
Okay.
and 60% for surface CO emissions.
Do you assume correlation also? Special correlation in your
No,
emission?
we did not consider any special correlation between the different point emissions. So the emissions at each grid point were analyzed independently. But of course, the observation used for the analysis of the different point emissions are mostly common, because we can use the observation located within the 2,000 kilometers from the analysis point. So the neighbor emission can have similar adjustment because of the use of the mostly common observational constraints. Yeah.
Thank our speaker again.